Hi, welcome once again to Math as a Second Language, where today we'll actually get to the language of fractions per se. And what's interesting is students have always said to me, I've always had trouble dealing with fractions. And the answer to that I usually give them is, so did our predecessors. But the beauty was that when you use words, when the numbers are adjectives that modify nouns, you can avoid having to use fractions. In other words, when we take a portion of a quantity, a smaller portion of a quantity, we don't have to say it's 1/3 or 2/5. We just give it a different name. Okay? So let me just show you a couple of things that I think are kind of interesting. They always seemed kind of special to me, and I thought you might enjoy that too. The word teen. It essentially means plus 10. So for example, 14 is 4 plus 10. Now, what's interesting is if teen means plus 10, why wasn't 11 called 1 teen? In other words, if teen means plus 10, why does the first teen come after 12 rather than after 10? And the answer is that prior to the invention of place value, 10 was not an important number. 10 just became important with place value because of the biological coincidence that we happen to have 10 fingers. Prior to that, people wanted numbers that could help them avoid fractions. That's why they put 12 in a dozen, because you could break 12 into fractional parts without breaking anything, easier than you could do that with 10 in a package. So in other words, 12 became the number that people dealt with. That's why they had words like dozen, and then a dozen was called a gross. Come to think of it, I think my name would be much more impressive if instead of Herbert I. Gross, it was Herbert I. dozen, but that's a different story. I just thought, anyway, we deal with a dozen, which is 144, okay? Why did we do that? Because it helped us avoid fractions. Here's another one. The prefix DEC stands for 10, just like in the word decimal. That being the case, why is the 12th month of the year called December? Why wasn't October, which is the 10th month of the year, why wasn't that called December? And again, what's interesting to note is that the original calendar had 10 months, each with 36 days. And the reason was that would make 360 days in a year, and 360 has so many nice divisors that it made many fractional parts of a year into a whole number of days. Of course, what happened is it raised heck with the seasons because you were losing like 5 days a year, and so eventually people corrected the calendar, but the ancient Greeks liked the number 360 so much that they decided to use that as to how they were going to break circles into fractional parts. In other words, by having 360 degrees to a circle, many fractional parts of a circle became a whole number of degrees. So, in other words, fractions were always popular, but they got around it by having the denomination be a word rather than a denominator. See, with enough nouns, there would be no need for fractions. In other words, if I could say 1 inch, why should I talk about 1/12 of a foot? If I can say 1 ounce, why should I talk about 1/16 of a pound? If I can say 1 minute, why should I talk about 1/60th of an hour? The problem is that in math, the numbers are adjectives, we don't see the nouns. So for example, there's nothing wrong with saying 12 inches equals 1 foot. Now, as long as we're dealing with feet, suppose we dealt with inches. Suppose we say, okay, there are no nouns appearing, but the noun that's going to be assumed is inches. Then I wouldn't write 1 foot. I would simply write 12 because the noun is understood to be inches. But what if somebody said to me, no, I want the noun to be feet? Well, if the inferred noun is feet, We can't have 1 stand for 1 inch and both 1 foot. Now we're dealing in terms of feet. An inch is smaller than a foot. What is an inch? It's 1 of what it takes 12 of to make a foot. So if the implied noun is inches, we have to deal with 1/12 because that's the only noun that we're allowed to use because there were no nouns appearing. Okay? Now, the importance of division comes up very, very important. You know, it's interesting. Division is the last operation we learn of the big four, but it's the one that's usually the most important. Many, many times you worry about how fast versus how much. If you're riding along the highway not paying attention, and all of a sudden you see the flashing lights of a patrol car behind you, do you glance at a road map or your speedometer? Do you care where you are, or at that moment are you concerned with how fast you're going? See? The rate is important there. I remember the story that was told as a joke about the driver who stopped because he's going at 70 miles an hour in a 30-mile-an-hour speed zone. And the officer said, "Do you realize you were driving 70 miles an hour?" He said, "Officer, that's impossible. I've only been driving for 10 minutes. You see, a rate isn't a time and it's not a distance. It's a ratio. It's distance per time. A rate is always 2 nouns separated by the word per. Miles per hour. And what does that mean? The number of miles divided by the number of hours. Dollars per pound. The number of dollars divided by the number of pounds. And you don't even need nouns that sort of seem to go with one another. You can talk about apples per lawyer. You're dividing apples among a bunch of lawyers. The number of apples divided by the number of lawyers is the number of apples each lawyer gets. Now, what's interesting is we can visualize everything just by dividing things into fractional parts. And I invent something. I say I invented it. I don't think I... The reason I invented it was that students found rectangles kind of abstract. They found it easier to deal with personifying the rectangle, so I called it a cornbread, because that was the first thing I thought of that came in a rectangular shape and was easy to divide into pieces. Have you ever... What is the usual way that you were taught to represent fractions? I was taught with pizzas or pies. You had a round pie, and you had to divide. 1/5 meant you divide the pie into 5 equal pieces. I never could do that. I always did it wrong. But it's much easier to divide a straight line, or cornbread, into 5 pieces of equal length. In fact, this is a nice way to introduce geometry at a certain level to your students. The ancient Greeks had a method of dividing any line segment into any number of equal parts. Let's suppose, for example, I wanted to divide the cornbread into 5 equal pieces, 5 pieces of equal size. One method I call the prayer method. I pick a length and I mark it off 5 times, and I pray that it ends right where it's supposed to end. That method doesn't work that well for me. The ancient Greeks came up with a very nice method. What they said was, let me pick my own line. I'll just pick any line I want, and what I'll do is I'll pick a certain distance and mark it off 5 consecutive times. So if I call this the point A, and this the point B, see, I don't know how to divide AB into 5 equal parts, but since this is a line of my own choosing, I can divide that into 5 equal parts. I'll call this point C. So the line segment AC is now in 5 equal parts. The problem is it's AB that I want it to be in 5 equal parts. And you see, that's where, see if I can, what you do is you take a straight edge and you connect point C to point B, and then you just draw all these lines parallel to one another. And since these 5 pieces are equal in length, these 5 pieces here will also be equal in length, okay? And the students can verify that. So it doesn't matter how many pieces you want to divide a line segment into, this method works. If I want to divide it into 17 equal pieces, I mark this off 17 times, do the same construction. Once you've done that a few times, you can just assume that you know how to divide the cornbread into any number of equally sized pieces, okay? So the question is, let's see what happens now when we look at division. Here's a rather simple problem. How many cornbreads does each person get if 6 cornbreads are shared equally by 3 people? Well, I think everybody knows that. You take the 6 cornbreads, divide that by 6 people, and you have what? 6 divided by 3 is 2, and it's 2 cornbreads per person. Compare that with how many cornbreads does each person get if 2 cornbreads are shared equally by 3 people. Now, if all you know are whole numbers, you can't solve this problem. Why is that? If 3 people are sharing the cornbreads equally, can each person get a whole cornbread? No. Each person can't get a whole cornbread because there are only 2 cornbreads. So people say, you can't do that problem. Well, that's again our plateau. We can either say we're going to stagnate down here, or we're going to find a way to get to the next level. See, you might not want to divide 2 cornbreads into 3 people, but is it important that you might have to divide $2 equally among 3 people, or the best you can do that way? Is it possible that you might want to divide a 2-inch length into 3 shorter pieces, each of the same length that adds up to the 2 inches? So here's what happens. We just showed that if the noun is cornbreads, 6 cornbreads divided by 3 persons is 2 cornbreads per person. I spelled breads wrong here. What if you had 2 cornbreads divided by 3 people? Well, obviously you can't give each person a whole cornbread, but can you divide the cornbread into 3 pieces of equal size? Yeah, sure. So now, instead of 2 cornbreads per 3 people, what do I have now? 6 pieces per 3 people. Notice that 6 divided by 3 is always 2 as an adjective. It doesn't matter whether it's 6 cornbreads divided by 3 persons, 6 pieces divided by 3 persons. The adjective part of the answer will always be 6 divided by 3 or 2. The problem here is that the answer is now 2 pieces per person, but the problem was, how much cornbread did each person get? Well, each person got what? 2 of what it takes 3 of. And isn't that called 2/3? Divide into 3 pieces and take 2 of them. In other words, if the noun has, if we're allowed to use words, we can say each person got 2 pieces. If the only noun you can infer is cornbreads, we have to say it's 2/3 of a cornbread, 2 of what it takes 3 of to make a whole cornbread. The problem is, this is kind of easy to see, I think, but the word pieces is subjective. For example, could I have taken the same 2 cornbreads and divided them equally among 5 people? Yeah, what I would do then is what? Divide each cornbread into 5 pieces of equal size and give each person 1 piece from each cornbread, saying 1 piece for you, 1 piece for you, 1 piece for you, 1 piece for you, just deal them out. So again, each person gets 2 pieces, but this time it's 2 of what it takes 5 of to make a cornbread. Isn't it sort of obvious that when you divide the cornbread into 5 pieces, each piece is going to be smaller than if you divided that same cornbread into 3 pieces? So in both cases, you're getting 2 pieces, but they're not the same size pieces. It's like if my doctor tells me I can only have 2 slices of bread a day, all I have to do is take a loaf and slice it lengthwise. And I have my 2 slices. No one told me how big the slices had to be. See, the idea is we don't want subjectivity. If the nouns are going to be left out, we have to have an objective way for people to know exactly what's meant. So if the assumed noun is something or other, and we want to talk about a smaller denomination, we have to introduce fractions. And that's all that we're really doing here. Here's the invention of common fractions. When you say 5 inches, what does it mean? It means 5 of what it takes 12 of to equal 1 foot. And to abbreviate that, we say 5/12 of a foot. What does 12ths mean? It means 1 of what it takes 12 of to make 1 foot. So 5/12 is 5 of what it takes 12 off to make a foot. To eliminate the word twelfths, we write it as 5/12, and 5/12 is called the common fraction, with 5 being the numerator, telling you how many pieces you're taking, and 12 being the denominator, meaning the denomination. Yeah, this is the part that's often tricky for students. They confuse 12, which is what the denominator is, with the denomination, which is twelfths. In other words, for example, because 20 is bigger than 10, greater than 10, they sort of instinctively feel that 1/20th should be more than 1/10. And it always reminds me of the little joke they tell about the man who was so grateful that he overcame an illness that he increased his charitable donation to his church from 1/10 of a salary to 1/20th of a salary. You see, what it means simply is that if the denominator is 20, you're dividing the cornbread into 20 pieces of equal size. If it's 10, you're dividing the cornbread into 10 pieces of equal size. And if you divide the cornbread into 20 pieces of equal size, each piece is smaller than it would have been if you divided the cornbread into 10 pieces of equal size. Now, the next part that's interesting is that the fraction, see, even though a fraction is itself a quantity, like 5/12, 5 is the adjective, 12ths is the noun, 5/12 is also an adjective phrase that modifies whatever the cornbread represents. So, for example, if I talk about 5/12 of the cornbread abstractly, all you have to think about is I divide the cornbread into 12 pieces, and I take 5 of those 12 pieces. Well, what if the cornbread now represented an hour? If the cornbread represents an hour, the 12 pieces represent 60 minutes. They're all equal size. 60 divided by 12 is 5, so one piece equals 5 minutes. So 5 pieces, which is 5 times 1 piece, is 5 times 5 minutes, or 25 minutes. You see, so in other words, you have 5 as an adjective modifying twelfths, then 5/12 as an adjective modifying the fractional part of the hour. Well, I think this is enough for today's presentation. So let's go to our practice problem to see if you get the gist of what we're talking about. And the practice problem is simply this: use the fact that there are 360 degrees in a circle to decide which is greater and by how much, 2/5 or 5/12. Okay? Pause the video, work on the problem, come back and watch the video, resume watching the video if you want to see my comments on the solution. Well, you see, to compare 2/5 and 5/12, if the noun is a circle, we replace the word circle by 360 degrees. So now we're talking about 2/5 of 360 degrees. And watch how the pre-fraction language comes in. How do we find 1/5 of 360? It's just another way of saying divide the 360 by 5. And that's going to be 72. That's the size of each piece. And now what are you going to do? Take 2 pieces. That's 144 degrees. Follow it again. I divide, the cornbread now is 360 degrees. Divided into 5 pieces, so each piece is 72 degrees. And I'm taking 2 of those pieces, so it's 144 degrees. Now what about 5/12 of 360? Now I'm taking the 360 and dividing it into 12 pieces of equal size. That's, I guess, 30 degrees each. Okay? And how many of those pieces am I taking? 5. And so 5/12 of the circle is 150 degrees. 2/5 of the circle is 144 degrees. Notice that this fraction problem has now been reduced to an equivalent whole number problem. I look at this and I know that 150 degrees is bigger than 144 degrees. So therefore what? 5/12 of 360 degrees exceeds 2/5 of 360 degrees. See, not only is it bigger, but I know it exceeds it by 6 degrees. And if I want the noun to be circles again, 6 degrees is what? It's 6 of what it takes 360 to make the whole circle. 6 goes into 360 60 times, so it's 1/60th of a circle. And now, because all the nouns are the same, I can leave out the nouns and conclude that 5/12 minus 2/5 is equal to 1/60th. And we're going to do that in more depth as we go on through the course. But again, the main idea here is to help the students internalize that fractions are nothing more than shorthand notations for operations with whole numbers, usually multiplication and division, and then addition thrown in, or subtraction if we're comparing different parts of the same thing. At any rate, as I say, this concludes today's lesson, and I will look forward to seeing you all again next time.